and then joined PhD from Leibniz Institute of Polymer Research in Germany, that is in University of Technical University of like Dresden. Then he moved to University of Erlangen for his postdoc, and recently he moved to IIT Mandi as a faculty member on Quantum Mechanical Center. So Vaibhav is going to speak for today's session on this fundamental of photo detection. And so I request Dr. Vaibhav and welcome Dr. Vaibhav for this FDP, and request to Miss, please start your talk.
Yeah, thank you for the introduction. So I will try to share my slides. So can you see my slide?
Not yet, Vaibhav.
Are you able to see the slides?
Not yet.
Okay.
So in my opinion, better to go for like entire window when you are sharing it.
Yes, so I tried to share the entire screen. Let me try again.
Sure.
So maybe, are you able to see it now?
It's just Vaibhav moving and I'm not able to see.
Okay.
Are you on full screen mode, Vaibhav?
Yeah. Um, mhm. So you are still not able to see the screen, right?
Yes, it is just I can see moving like Vaibhav is shared, but we could not see the
So,
presentation.
so once I move, it's go away, right?
It is black screen till now. Can you give me the right of host, co-host? Oh no, Vaibhav.
So from my end, it's showing that it's, I mean, my screen is there. Or maybe can I try to sign in again?
Okay, please try.
Yeah, let me sign in again, maybe.
Yes, Vaibhav.
Yes, sir, I will try now.
Sure. Yes, Dr. Vaibhav, now it is perfect.
Okay, yeah. So thanks a lot.
Is good. Yes, perfect.
So good afternoon, everyone. Um, so you already know me, and thanks for the introduction. So let's begin with today's topic, which is the overview of photo detection. So I will show you some images and I will give you some relevance about it, like what is the photo detection and why should we focus on photo detection and what are the things related to that. So on this image, I hope you could see my cursor. So on this image, what you see is the mirrors of a telescope. And each mirror, so this one mirror itself, the dimension is in meters. And if you combine maybe 7, 10, 12 together, this is the telescope mirror for James Webb Telescope. And scientists try to put this in the space. And the aim is that the aperture will become quite big. And then maybe there is a star or galaxy far away, and some light will try to come and hit onto these mirrors. And then we can transmit that signal back to the ground station. So this is one way to do photo detection. In the end, the light is coming and we are detecting something. The another example, here you could see on the top panel, this is the satellite view image from year 2016. And then with time, you see what is happening is this solar park is getting bigger and bigger. So this solar plant is in Rajasthan itself. It is one of the biggest, and these kind of solar parks are also one of the example of doing photo detection. So usually here, what we try to do is we try to convert the sunlight into the electricity. But overall, what is happening is photo detection, meaning some photon is getting detected. Finally, what we convert into it, that is a different thing. We convert into electricity or we convert into a radio wave or something else. That is different. But in the end, the main point is that we detect the photon. So let me go to the third example. So most of us, we go to the eye doctor, ophthalmologist, and sometimes they suggest to do this optical coherence tomography. So what you have seen, placing your chin here, and then some technician is taking a lot of images of your eye. So what they usually do is that there is an infrared light at the back, and this light comes and it penetrates through the retina, and then they try to take cross-section image in depth through the retina. So that is also one kind of photo detection. Let me show you one example. So here is the image. That's what you see on top is the left image, left eye. OD means the left eye in Greek terms, and OS is the right eye. And this is the retina image of a patient, and this is a diabetic patient. So this patient has diabetes. The very first time the patient goes to the doctor does OCT, and that is the image of the retina of the left eye, and that is the image of the retina right eye at the very first visit. After the 4 months, the patient again goes to the doctor, and then the patient again goes through this OCT. And what doctor finds out, if you look here, this particular region, 4 months back there was nothing, but now you see what has happened here. So there is a lot of vessels which has created, and this is typically happens in the patients which are diabetic. So this can create in the end a problem that your retina will get detached, and you can also get blurry eyes. So what I just want to convey, my message is that this is again the photo detection, but now the detection is coming in terms of images and in terms of medicine. So I have given you example. Very first, the telescope was from astronomy, space science. The second one was, let's say, sustainability and solar. And the third one is medical devices and medical technology directly applicable to humans. Um, the other example is charge coupled devices. So the cameras which we use in everyday life in our mobile phones or the back panel of our LED TVs, they all have these detectors, which is again the mechanism they work on, even though they finally gives a video or an image, but they usually detect the photons. And then this is the example from Core Lab, and this is a device which can again calculate the power which is being transmitted into a fiber. So suppose we all use internet at our home and some router is placed somewhere. So if there is no internet coming, the very first thing the technician will do, it will check how much power at the output is coming. So they will come with some sort of this device, and then they will try to attach the fiber into this knob, and then on the other one they will attach their spectrometer, and then they will see how much power is there. So these things are in everyday use, like we everyday use these things. So photo detection, I hope I have given you some relevant example which might give you some sort of curiosity. So now let me go back to the historical background, little bit of history about this. Um, so in the very beginning, um, the cameras and all, they all started with understanding of the ray model. So what scientists choose to understand is that every object emits light in all possible directions, here, there, everywhere. So we have a smiley face, then we have an aperture, and there is a screen. And what you could see, that light comes in a straight line. That is the very basic prerequisite in the ray model, that light always travels in a straight line. There is no wave analogy towards it. So the light comes from here, light goes from there, and here we will get the image, which is the inverted image. And by doing this, you can still explain how the objective lenses work, how the camera works. That is fine. But this method fails to explain, let's say, the interference pattern. So in 1800, another theory came up, which was that the light is not only propagating in terms of rays, but they propagate actually in terms of waves. So what was the problem with the ray model? The problem is that the ray model says that if something is like this, just assume it as a straight line. So they just tend to move towards zero. Like if wavelength is going very small, they just say make it limit tends to zero and then make it consider this as a straight line. But if you want to explain, let's say interference, fringes, diffraction, and all those effects, this model does not hold, the ray model. Then after this wave optics, in 1830, Maxwell came up with the electromagnetic equations and all the Maxwell's equations. So what we have also studied in high school is that power is energy divided by time and intensity is power divided by the area. And finally, we can write the energy in terms of intensity, area, and time. So that means energy doesn't really depend on the wavelength, it depends on the intensity and the area and the time. This is what the whole classical picture says. So let's say if this wave is propagating, I can also write the electric field of the wave, where omega is the frequency, k is 2 pi by lambda, it's going into the z direction. Similarly, I can also find out how much energy the wave is storing in a particular area. So this is dependent on the electric field, magnetic field, and the permeability of the medium. And you can also go for the per unit area per unit time, which is the towards the Poynting vector. But this all was the classical picture. The main thing happened in 1905, something called photoelectric effect, and Einstein did a very major breakthrough, and he got the Nobel Prize for this in 1921. So what he tried, or let me just explain you briefly. Suppose we have a vacuum chamber and we have two electrodes, one here, another one here, and we apply a particular voltage or some battery. What we expect is that there should be some current flowing, but it will not flow because in the vacuum there is no medium, so definitely there is infinity resistance here. What they tried is that, okay, let's hit one of the electrode with one particular light, and maybe the electron will come out, and then this electron will go through this medium because the kinetic energy will be very high and the circuit will be complete, and we will see something voltage in the voltmeter, some voltage will pop up. This was the idea. So they started hitting some photons on this electrode. So let me take this electrode separately. Suppose it's a gold electrode, and I start with a wavelength of 1064 nanometer, and I know nothing about photoelectric effect and all that. I just know that energy is intensity, area, and time dependent. And what I know is that if I want to eject one electron out, I just have to hit with a particular wavelength and with particular energy. And this energy is dependent on intensity, area, and time. So I start with lambda 1064. This is the area where my light is hitting. So the spot size of the light. And nothing was coming out. So I thought, okay, let's increase the area because that is what the equation says. So I increased the area. Again, I don't see anything on the voltmeter. Nothing is happening. So again, I see that they say increase the intensity. So rather than one photon, I started hitting with billions of photons with 1064. Nothing is happening. Then another thing is time. So I thought maybe let's do it not for 5 minutes. Let's do it for 10 minutes, 1 hour. But still, I don't see anything. So that is very troublesome because it looks like all the laws of classical physics and classical mechanics started to fail. And then what they thought, okay, let's try to reduce the wavelength. So let's try to hit a wavelength close to 259 nanometer. And once they do that, they see that the now electrons started to come out. So that is very counterintuitive because this has never been explained. It seems like energy is somehow dependent on frequency or somehow dependent on the wavelength, and this formula doesn't say anything about the frequency or the wavelength. So the main outcome is that if you have energy which crosses the work potential of the gold electrode, then definitely you will eject the electrons. Electrons will come out, circuit will be complete. The proportionality constant here is H, and this is called the Planck constant. And there was a scientist called Millikan. He found out the value of this constant. So that is about the photoelectric effect, and that is the backbone of all the semiconductor devices what we use in today's time, be it the chip, be it the motherboard of your laptop, be it your mobile phones, whatever you use, 24 nanometer NOT technology, 4 nanometer, 2 nanometer, the basic backbone is this effect, and because of that he got the Nobel Prize. But there is another one interesting problem, and I will leave you with that problem. I will not solve it. So this now says that, this is called wave particle duality. So now I can consider light as a particle. I can call them photons. So if light is a particle and we call them photons, so Newton says that the energy is half of mv squared. This is what we know. So energy is in terms of if I have one photon, then the energy should be half of mc squared. But I know that the mass of photon is zero. So then the energy should be zero. So this again creates a problem. So you can think about it, that what is the logic behind it, that why this equation is true, but what is the contradiction between the Newton mechanics and the E equal to mc square. But I just wanted to tell you that there is some history behind photoelectric effect, and this relates with the Einstein's experiment, and this gives the backbone for the semiconductor physics. So now let's go to the main topic, which is the photodetection. So what is the photodetection? The definition is that the conversion of photons in terms of either the electrical signal or the voltage or image or thermal, you just convert the photon in any other form. I will call it a photodetection. And how this process works? So the very first thing which is very important is that first I must absorb the photons which are of my interest. I should be able to absorb them. The second thing is the carrier generation. So once the photon hits, it will do some sort of electron hole pair generation, and then I should be able to capture those electron hole pair. It should not be like that they recombine and then go away. And then finally, I should be able to measure some current or voltage. So that is the process. So here is a basic diagram which is used for photo detection. So it is a PN junction. Here is the P side. It's a semiconducting material, and here's the N side. And this is the depletion region. As soon as I apply reverse bias, so the N side is connected with the positive terminal, that is the reverse bias, the depletion region is automatically broad. And now if I come with photons, and if I hit this depletion region with some particular photons, what I see that electron hole pair will get generated. These electrons, they will try to go in this direction because they will be attracted towards this positive terminal, and then finally the current will be in opposite direction. So as I said, absorption meaning catching as much photons as possible. Then we have to do this carrier generation, meaning generation of these electron hole pair and extraction of them into the final circuitry, and then finally measure this current here. So that is the basic principle. Now, how to enhance the absorption? Um, so let me first say, this is very basic, that the photons which you are using must have the energy which is above the band gap of your semiconducting material. The second is the anti-reflection coating. Why anti-reflection coating? Because consider that a lot of photons are hitting. It's not that photons are only hitting at this area. It's likely that photon might hit other areas as well. So the photon might also hit here, the photon might hit here as well, and simultaneously they will also reflect and they will also transmit through it. So if I want a good detector, I don't want any transmission. and I also don't want any reflection here. So for that, I need to use anti-reflection coating. So all the photons which I want to absorb, they should not go away. So that is one thing. Now, how much should be the thickness of this anti-reflection coating? That's a different thing. Usually it's lambda by 4 and the multiple of lambda by 4, but this one can understand. Now comes the type of photodetectors. So there are different type of photodetectors, and in today's lecture, I'm mostly interested on these kind of semiconductor kind of photodetectors. So what are the other ones? What they can do is that if you hit the photon in a thermal detector, usually the temperature will change, and then you can detect this temperature change. They will respond to the temperature change. Some pyroelectric ones may be a response to the polarization change. But what basically we are interested into the photodetectors, which are semiconductor based. So I will just divide them into different parts. One is photoemissive and another one is photoconductive. So what is photoemissive? Photoemissive is the one when you incident a photon, usually it generates an electron, and this electron will do cascade effect, and then it will kind of do a burst process, and a lot of other electrons will get generated. So this is typically called photomultiplier tube, and they have very high sensitivity. The another one is photoconductive type, and in this one we have three different types. So photoconductor is the semiconductor as it is. So we just apply some voltage to the semiconductor, electron hole pair is getting generated, and you just collect them. And the photodiodes have basically two different types. One is PIN and another one is avalanche photodiode. So in today's lecture, we will basically focus on these two. So there are some key parameters, and mostly we stick to those parameters. Suppose we go to the market and we want to purchase some photodetector. So there are certain parameters which we will look for. Or if suppose somebody is a device engineer who is trying to make a device or a photodetector, that person, he or she will look into these parameters and try to maximize these parameters. So what are these parameters? The very first one is the responsivity. One can also call it external quantum efficiency. It's a conversion rate, like how many photons you have converted into the electrons. That is the responsivity. The quantum efficiency, which is you can also call internal quantum efficiency, and I will come back to this in more detail, but usually we would preferably we try to have it one or more than one. Then the rise time, this actually defines how good is your detector. So suppose I hit a photon, how much time it takes to show me the current value. Is it showing me in 5 minutes or 1 second or 1 nanosecond or 1 femtosecond? So faster the detector, better it is. Then comes the dark current. So the dark current is kind of a noise, which we will discuss in more detail when we will discuss the noise. But dark current is simply the current value when there is no photon incidenting on the detector. And finally, the last is NEP, noise equivalent power. So you can understand that this is NEP is the value of the photon energy or the photon power, which is equal to the noise power when the SNR ratio becomes 1. So just to make it simpler, if NEP is lower, the detector is very sensitive. So usually you have some noise into the system, and how much photons should I incident on the photodetector? How much photons should I incident to the photodetector so that the power of these photons is equal to that noise? So actually at the NEP level, you will not be able to distinguish between the signal and the noise because your signal is exactly equal to the noise. So that is called the NEP. So you can consider this as a kind of least count of the device, and then below that it cannot detect anything, and then above that it is able to detect things. So now let's go one by one into these parameters. So here again, I will always use this circuit, mostly try to use this circuit. So what we have here is this photocurrent. which is getting generated because we are incidenting some photons, and these photons have some incident power P. So P will be equals to N into H mu. So if one photon has power equal to H mu and I'm coming with N number of photons, so P is equals to NH mu. And then the total power is P input. And if I already told you the responsivity is IP divided by P, so this becomes RD becomes my responsivity. So this is actually the conversion rate, meaning how much of this optical power is getting converted into the electrical current. Now comes the another part, which is the quantum efficiency. So quantum efficiency is the electron generation rate divided by the photon incident rate. So if you look, it looks somehow like that this thing is exactly the same thing. What responsivity is kind of giving to me, it's the same what is quantum efficiency is giving to me. So actually you can say that because in a way they both are related to each other, and you will see that in a minute. So what is the electron generation rate? So if I know the total current, the current is number of electrons multiplied by its charge. So if IP divided by the charge, I will get the number of electrons flowing, and I will also get the number of photons incident if I just divide by H mu, because I said P is equals to NH mu. And if you do the math, you will find out that the quantum efficiency is now related with your responsivity. So here you know H is a constant, Q is a constant, and mu is also C by lambda, and C is the velocity of light. So this is again dependent on the wavelength and the responsivity. So they are related with each other. So finally, you can write the responsivity in terms of quantum efficiency and the wavelength, which is in micrometer divided by 1.24. This is very commonly used formula for the responsivity. So now there are some questions which automatically arise, and these questions are, how can I increase the responsivity? Meaning, I want most of these incident photon to be converted into current. So how should I do that? As soon as I ask the first question, and if I look at the equation, I see that it's depend on the lambda. So if I increase the lambda, automatically the responsivity will increase. So the very first answer comes in my mind. If I want to increase the R, just increase the lambda, and then R will increase. The second question, the second answer comes in my mind, or maybe try to increase this quantum efficiency neta, and then also this responsivity will increase. But then what are the factors on which this neta depends? Because this might also be depending on some factors. So I have to take care of those factors as well. If I want to maximize this value, so maximize lambda and maximize neta, and then everything will be fine. And the final question is, why does this responsivity is increasing with wavelength? These are some questions which should definitely come in our mind after looking into this equation. And if suppose you give this problem to some design engineer and say that I want very high responsivity, he or she will definitely look into the equation and think that, okay, let's try to increase these things and we will get very good responsivity. So let's try to answer the last question, that why this responsivity is increasing with wavelength. And is it possible that if I keep increasing the wavelength and then I can get infinite responsivity? So this is the formula, and here's the question. So let's try to take two different cases. The very first case where the wavelength is lower, so energy is higher, and here the wavelength is higher, so energy would be lower. And let's say the incident photon have 1 milliwatt of power. So in both the cases, I'm using same incident photon power. As you know, this formula NH mu. And what happens is you can also write in terms of lambda. So what is happening? Lambda I have increased, Once I increase the lambda, the mu, the frequency goes down. So actually, if I increase the lambda, this is a constant, which is 1 milliwatt, right? So the LHS, left hand side, is a constant. Here H is also a constant, and I have reduced mu. So automatically I will increase N in order to keep LHS equal to RHS. So what happens is that in this particular case, the number of photons automatically increases to maintain the same power. And hence, as you know, that if we have energy which is more than the band gap, and we have more number of photons hitting to the photodetector, definitely then the responsivity will increase. So this is what is happening here. That number of photons will be more for the same power for this particular case, and here number of photons will be less as compared to this. So then another question which I already asked, like, is it possible that I keep increasing this lambda and get infinite responsivity? So that is also not possible. We have to respect this condition of the band gap. So if you keep on increasing the wavelength, I told you that E is inversely proportional to lambda. So the energy of your photons will go down, and as soon as it goes down to Eg, it will not work, or your photodetection will not work. So we cannot increase the wavelength. So here I have taken a graph from Thor Labs, and what this is a responsivity versus wavelength, and this is an in-gas detector, and you see that for 1550 nanometer, which is the telecom wavelength, the responsivity of the detector is quite high, which is roughly like 1.1. So this is a very good detector for near infrared or 1500, 1600 nanometer. This is a very good detector. It can also detect 1100 nanometer, but then the responsivity will be lower. But this detector is not good for visible wavelength 600 nanometer. We will not use in-gas detector. So this is what typically responsivity curves will tell you. Now there are two questions. Why this curve is suddenly dropping down at this particular wavelength? So as I told you, we have to respect this Eg, or the incident photon must have the energy more than the band gap. So if you keep on increasing the wavelength, at one point you go the energy which is lower than the band gap. So that is the upper cutoff. But another question here, the wavelength is quite low. So that means the energy is high. If I keep moving in that direction, maybe 300 nanometer, ultraviolet and all this, so they have very high energy. But then why the responsivity is going down? Because they respect the law. Like, because in those cases, the energy E is greater than the band gap energy. But then again, the responsivity is decreasing here. So this is okay. This I understand, but I don't understand this part, that why it's decreasing on this side. And also please remember that the responsivity value is not like the maximum is 1. It can actually go more than 1, and even it can go up to even higher values. So as I asked you why the responsivity is going down at this particular case. So we will come back to that. But before that, I will show you one more thing. So for the visible wavelength range and visible to near IR, we usually use silicon photodetector. So this is again responsivity on the y-axis, wavelength on the x-axis, and we have a curve for silicon photodetector, and this detector works very well at 700 nanometer. But again, the same thing. Here is the cutoff, and here is the problem, which we don't understand. So why the responsivity is poor for silicon detector? So this is one more question. If you look at the values, here the responsivity was 1, right? For in-gas detector, which is used for 1500 nanometer. Here, for the visible wavelength, look at the responsivity. The maximum is roughly 0.4. So responsivity is poor as compared to in-gas detector. But why this responsivity is poor? So the answer is that it's an indirect bandgap material. Silicon is an indirect bandgap. And also the answer is somehow lies in the absorption coefficient. So we will also discuss that in a minute. Um, so to try um, to answer these questions, that why the responsivity in silicon detector is poor, why it's decreasing for the wavelengths which have very high energy, and what is the relation with the absorption coefficient and direct band gap indirect. So let's try to answer these questions. Let's go back to the very basics. So again, we have this p-n junction. Um, Photons are coming. It is in reverse bias, and we have this depletion region. When the photon hits, we have electron-hole pair generated, and then we have to extract them. Once they come out into the circuit, we measure the current, and that is this current. Now, uh, let's let me try to focus only on this depletion region. Okay. So I will take this region out separately here. That is the width of this depletion region. And let's say this is the incident photon power P in, and the photons will go through this channel, and then some will get definitely transmitted, as I also showed you in the beginning, and some might also get reflected as well. So how much would be the transmission? So this Beer-Ambert law, very famous law, we know that the transmitted power would be e to the power minus alpha W input power. What is alpha? Alpha is the absorption coefficient of this material. What is W? W is this length. So if I want to make a good detector, what do I want? I want that this transmission should be very low. I don't want any transmission, because if light is transmitting, what is the point? I want most of the light to be absorbed inside the system. So actually what I want is that this value should go close to zero. This should go close to zero. This is my aim. How can I do that? So input power, this I cannot change. Maybe that dependent on the photons. So this is the things which are in my hand. So e to the power minus alpha W. And if I make this number very small, automatically the overall number will be small and the transmitted power will be very small. So how do I make this e to the power minus alpha W small? Two options: make the alpha very large, and second option, make the depletion region very large. And then less transmission will happen, only absorption will happen, and that's very good for the detection. So as you know that we also studied the quantum efficiency equation, and now I will try to relate this whole thing with the quantum efficiency. So you remember the quantum efficiency was electron generation divided by the incident photons, photon rate. So the electron generation, can I write it the absorption power, like whatever light which is getting absorbed, only that light is actually contributing to generation of the electron hole pair. So finally, if I get P absorption, that is actually the electron generation rate. So if I know the transmission value, what I need to do is I just subtract it. 1 minus transmission will give me the absorption. Forget about the reflection for the time being, because we know that reflection plus transmission plus absorption, everything should be equal to 1. So I can write like this here. And then if I subtract 1 minus e to the power minus alpha W, and that will give me the absorption thing. So this is here, only focus here. So this is the part, right? But you see, I have written some other things as well. And you remember in the beginning, I also told you that I will tell you in detail what is the difference in quantum efficiency and responsivity. So actually responsivity is basically the external quantum efficiency. And quantum efficiency, when we say quantum efficiency, that is the internal quantum efficiency. Now see what is happening. So So let's say some photons are hitting, right? And very first thing you have to understand that the photons which are actually hitting on this active depletion region, only they are contributing to electron hole pair generation and to the final current. The light which is hitting anywhere else, it's not really contributing to any sort of um, photo detection, you know. So when we calculate responsivity, we consider usually all the photons, but when we go towards quantum efficiency, we have to consider P absorption, meaning the photons which are getting absorbed, but out of these absorbed photons, which are these, we also have to multiply it with some factors. So the first factor is the reflection coefficient, which is, suppose this medium has refractive index n1, this has refractive index n2, um, and then there will be some reflectivity. So you have to multiply, and this will be definitely less than 1. So this will go down this number. So the total photons which are absorbed, all of them are not contributing. Some of them first get reflected, okay, fine. But what is getting absorbed, some of them is this zeta term. So what happens is that some of them will generate some electron hole pair, and this electron hole pair will just recombine here itself and give the energy in terms of heat or phonon. This is not giving anything in terms of current or contribution towards the current. So we don't want these kind of carriers, or they are unnecessary carriers. But you cannot avoid it; it will be there. So remember, these factors zeta will also be there, and this factor is less than 1. So when we consider quantum efficiency, all all the photons which are getting absorbed, they all do not contribute to photocurrent. This we have to understand. Some of them, what happens is that in semiconductor we have a lot of, so we have conduction band, right? And we have valence band. Um, and below the conduction band, there are a lot of trapped states or surface defects. And lot of carriers will go and then sit here rather than going up and then contributing towards current. And then once they stuck here, they are no more contributing and coming back to the circuit. So that is one more problem. So the photons which gives their energy in terms of phonons or heat, the photons which uh, gives electron hole pair, which to trap state or surface state, and they don't recombine uh, in a way like they recombine, but they don't give, so they don't come back into the junction. We have to discard them when we calculate the quantum efficiency or internal quantum efficiency. When you calculate the responsivity, it's fine, you can keep them. So um, now when you write this RD formula, you have all these factors. And now if you want to increase your RD, you have to keep an eye on this. How to improve this value? So make your semiconductor um, fabrication very smooth, very nice. So if I say TiO2 has Anata space, so it should be very crystalline, highly crystalline, take it to high temperature, and there should be very less impurity, there should be very less vacancies, and there should be very less trap state. And that's how you fix this problem. The another thing, the W, so meaning you have to improve the channel width, and we will see how you increase this depletion region. And the third thing, use the material where you have very high alpha or the absorption coefficient. There are these parameters which one has to take care when designing the material for photodetector. So what is this alpha? Um, so alpha is material dependent, and depletion region you can actually make a pin diode. I will talk about it later. So here what you see is we have two materials, silicon and germanium, and here is the alpha, which is the absorption coefficient, and here is the wavelength. So you see we usually use silicon for visible wavelength detectors. Now silicon and germanium both are indirect band gap. A typical question should come in your mind that I just said use very high absorption coefficient to make a good photodetector, but it seems that germanium has very high absorption coefficient. So why are all the detectors are made up of silicon for visible wavelength? Why not germanium? Why are we not using germanium? So there are some answers which are dependent on, some are dependent on the availability. So silicon is very vastly available. It's in abundance. Germanium is not. The second thing, all the chip fabrication, CMOS technology is based on silicon platform. You have seen silica wafers and all. Rarely you have seen germanium wafers. The third very important thing is that the band gap of germanium is roughly 0.7, and silicon band gap is higher, which is 1 point something. So what happens at room temperature, if temperature increases too much, um, the temperature itself can give dark current because of the low band gap, and then automatically you started having current without even incidenting any photon. So you can have a very high dark current. That's why people try to avoid the germanium and try to use silicon. So that is one reason. Um, now, the second question I will try to answer. The question is, what is happening in these areas where we have very high energy? This energy is even beyond the band gap, but then why responsivity is going down for these wavelengths? So here you see that is the diagram of indirect band gap material. So we have a conduction band and we have a valence band, and what you see here is uh, so that is not aligned, right? In a direct band gap material, it should be like this, but there is a mismatch. So that is typically indirect band gap material. Now, what happens? Suppose you take a wavelength, let's say 300 nanometer. Correspondingly, it will have a very high energy, which will be definitely more than the band gap. So we have very high energy of photon, which is more than the band gap, and some carrier moves from here to here. Now, this carrier has very high energy. We call them hot carriers. And what happens in the end is that this carrier will end up losing its energy um, in terms of lattice collision. So what happens that if this is silicon or N or type P type material, if it goes high, with a very high energy, it will recombine non-radiatively. So it will not give the energy or back in terms of, let's say, giving light or giving electrons and coming out into the system, but it will just stay into the lattice and do some sort of phonon vibration collisions, and it will decay non-radiatively. And this decay will be very fast, maybe in femtoseconds. So it's very hard to extract these kind of carriers which are generated with these kind of photons. So that is one reason that the responsivity is going down, because we are not able to extract those carriers. The carriers which are generated with these photons, usually these carriers decay in terms of heat, and this decay process happens within femtoseconds. So we don't really have chance to take them out in the circuit. Um, so this is phonon mediated. The second thing, you see the absorption coefficient, let's say for silicon, it's very high for lower wavelengths. So for 500 nanometer, it's quite high. So that is the another reason. So the another reason is that what happens if you use a wavelength 300 or 400 nanometer, since the absorption coefficient is very high, there will be a lot of dangling bonds which are sitting here on the surface. So there will be a lot of dangling bonds. And what happens is that your um, photons which will hit to the surface, they will trap on the surface, or they will stick to the surface because of very high absorption, and they will not be able to go deep down inside and do some sort of electron hole pair generation and then coming out. So that is another reason that we have a cutoff on the higher energy side or lower wavelength side as well. And this I already told you, this is because we have to respect the EG law. So that is all about the about this photodiode lecture up to now. So maybe now I will talk um, a little bit about the rise time and the bandwidth of the detector. And before that, maybe we can take a break of 5-10 minutes, and then we can come back.
Okay,
So is
Dr. Weber.
it?
Yeah, this is Manoj.
Hi.
Yeah, actually, can you take one or two quick questions? There are some two questions basically.
Sure. Yes.
Yeah, so you can also see directly in the chat box, but I will read it here. So the first thing is uh, there is question that I have a doubt. Can a photodetector generate a current in complete darkness? And similarly, can a photodetector be damaged by very low intensity light if exposed for a long time?
Sorry, sir. I think your voice is kind of echoing. So I was able to understand the first part, that can it give the current even in the complete darkness, but I was not able to understand the second question.
The second one actually is if we keep some photodetector for a longer time in very low light, will it damage the photodetector? Can it damage photodetector if it is kept for very long time in low light?
I'm sorry. I think I still cannot
Okay, so
understand. Oh, okay. Have you written in the chat? Is it the question?
yes, these are the questions from the chat itself. Can you go through the chat?
Okay. Yes. I will open the chat. Yes. Can you explain the slide 16 again with regard to decrease in the responsivity? Okay. As wavelength increases, the energy decreases, and this energy is not sufficient to generate new electron hole pairs for responsivity. Okay, someone already answered. Not audible. Okay. Mhm. So yeah, the very first question: can a photodetector generate a current in complete darkness? So the answer is yes, it can generate a current in the complete darkness, and this will come into the noise part actually. So the current itself is not only dependent on the photon which we incident, it's also dependent on the temperature inside the room. So if I increase the temperature, then we will have a very high current values. So this is a part of noise. Um, you can say, okay, if something is only coming from photon, and if there is no photon, I would say dark. Dark doesn't I mean, it's just the word. It doesn't really for to say that if there is, even if there is no photon, it is possible that definitely the photodetector will have current values. I will show you. Can a photodetector be damaged by a very low light if exposed for a long time? So for this, um, I think the answer, it cannot be. So you have to have increased the light, which should be more than the threshold. I mean, if it also depends how long you are keeping the detector exposed. So then the problem will come from the dark current side, not from the light intensity. So if the working window is 500 to 800 nanometer, if you keep hitting 560 with a very low intensity for 1 hour, 2 hour, 3, 4 hours, that is no problem. Uh, but then once the device is started to heat because of that, because let's say we do not cool it properly and there is no direct cooling available, then the problem comes due to heat management and device packaging that side, and then it can damage. But I mean, every question has different. So in that sense, it will not damage just because if you forget to close the shutter or close the cap, and then it exposed for 5-10 minutes or 1 hour, it will not get damaged. As wavelength increases, the energy decreases, and this energy is not sufficient to generate. Yes, so Ranjan, yeah, this answer is correct. Can you please explain slide 16 again with regard to the responsivity at lower wave? Yes, I will do that now. Can radiation space lead to increase in the dark current? Yes, that is true. The cosmic radiation space can lead to the increase in the dark current. But in the space, the good thing is that we don't need to do active cooling. So because the temperature itself is quite low, but still, if there is some sort of storm or something in the space, then it can definitely create a lot of noise into the system. So let me go back to the
Sorry to interrupt you. Maybe we can have a break for 5 minutes. And before starting the second lecture, you may address the queries. People may post the queries here till then, or you can address.
Okay,
like,
okay, sure,
Okay,
sir. Sure, sir,
okay.
sure. I will do it.
So we
Okay.
will have a 5-minute break, and then we
Yeah.
are meeting again for the second lecture by Dr. Vaibhav Gupta. Thank you.